And here we are. After this initial, let's call it introductory part of the webinar, we are coming to the central part where we are going to talk about the fundamentals of acoustic design and the strategies on how to include acoustics in the architectural design. There are 5 fundamental aspects of acoustic design. So for every single project in the world, no matter of its type, of the size or location, there are these 5 aspects that we have to consider in order to address the entire acoustic design of a certain project. And we can use this image of a very simple object to illustrate all the 5 aspects. The first fundamental aspect of acoustic design is maybe the one that everyone is the most familiar with. That is the sound insulation between the interior spaces of the building itself. Second one is the room acoustics, which refers to the quality of the sound within the space. So that would be something along the lines of the acoustic ambient in the restaurant examples we have discussed before. Third one is the insulation from outdoor noise. So basically the design of the building envelope to provide sufficient insulation from the outdoor noise. Next one, the noise of building services which are heard inside the building. Those are typically air conditioning systems, ventilation systems, plumbing, elevators, and various items of equipment which are essential for the operation of the building. And the last one is the impact from our building towards the environment. So this aspect deals with the acoustic treatment of equipment which is installed within our buildings or typically on the roofs of our building. So no matter how complicated the project might seem, the acoustic design and the acoustic challenges can be always broken down to these 5 fundamental aspects. So let us start with the first fundamental aspect of the acoustic design, the one that is maybe the closest to everyone, that people usually have in mind when we talk about acoustics. That is the interior sound insulation. At the beginning, it's very important to define 2 principal mechanisms of sound propagation. One is the airborne sound, and the other one is the impact sound. The airborne sound is the sound which travels through the air. So that would be the sound that we hear when someone is singing or listening to the television. On the other hand, there is the impact sound which travels through the structure. And that would be the sound that we hear when someone is walking on the floor above us. So when we talk about the airborne sound and the ways to protect ourselves from the airborne sound, to isolate ourselves from the airborne sound, we use this term airborne sound insulation and we denoted it with RW. And we say that the higher this RW is, the better it is. And to give you an idea what this means, we shall illustrate the subjective impression of privacy for some basic constructions. So now let's imagine that the person on one side of the wall is talking and we are listening on the other side of this wall. And the wall between us has a certain RW rating, so it has a certain airborne sound insulation rating. If this wall has an RW rating of 30 decibels, which would correspond to a typical glass wall, we would be able to clearly understand the speech, even if this speech was at a normal voice level. Now, if we change this wall and we build a better one, which has the RW of around 40 dBs, which corresponds to a basic dry wall without the mineral wool inside. Now, we can still hear the same conversation, but we would struggle to understand it this time. So this level of insulation is usually considered as the basic for the office space. Now, if we move even further, we upgrade our wall to RW of 50 decibels, maybe just by filling this dry wall with the mineral wool insulation, we come to the point where the normal speech is not longer heard. And this level of insulation is usually considered as the basic for residential spaces. However, this does not mean we will not hear the neighbors if they talk a bit louder or if they decided to play some music. So we would have to go further up, let's say to 60 decibels, to make a loud speech not heard. And this wall construction, which could provide 60 decibels, could be, for example, a dry wall with a double stud construction. So you can see that there are very, very fine limits between these ratings, and all these are actually subjective. So it's not easy to make everyone happy all the time. And this is exactly the part of the story on the difference between the acoustic regulations, which maybe stand around the level of 50 decibels, and the acoustic classes, which could go even above 60 if we decide to build a project worthy of a luxurious acoustic class. So to remind ourselves, the higher the airborne sound insulation, the better it is. And the principal design strategy when we talk about the airborne sound is the careful selection of constructions which have high airborne sound insulation. With the impact sound, the situation is slightly different. Acoustic regulations will generally regulate the level of the impact sound. So just be careful, not impact sound insulation, but just impact sound. And for this impact sound, the lower the value, the better it is. To put things again into the perspective and to understand this a bit better, let's take a look at the value for impact sound for some typical floor constructions. If we have a simple concrete floor, we could expect the noise level of around 80 decibels when someone is walking on such a structure above our heads. Of course, this level will be very much different if someone walks with the soft shoes or high heels, but in this case acoustic standards go so far that they define the standard level of impact sound, and such standard level is something more closer to the high heels than to the soft shoes. So if we go to the next step, we upgrade and install the ceiling with the mineral wool below this concrete floor, we can now expect an impact sound of around 60 decibels. In case we did such an upgrade on the upper side of the floor, so we structurally separate the concrete floor and the finished floor level with the mineral wool layer, we can expect an impact sound of around 50 decibels. And if we pair these two solutions, so we provide the floating floor above the concrete slab and we provide a ceiling below the concrete slab, we can now expect an impact noise level to go even below 40 decibels. So although it's the impact sound which is generally regulated, and yes, we target the lowest possible figure for the impact sound, it's actually another quantity which material manufacturers will generally talk about and publish. And this is the delta L value, which is actually the reduction of the impact sound. And this is nothing more than the difference in impact sound between the concrete floor and the same concrete floor upgraded with a certain solution. So for example, our floating floor has delta L value of 30 decibels. Our ceiling solution has a delta value of 20 decibels. And in this case, the higher the delta value, the better it is. So impact sound and reduction in impact sound are therefore two very similar things which usually cause a lot of confusion in the design. But what's very important to remember is the lower the impact sound, the better it is, the higher the reduction in impact sound, the better. And the principal design strategy will include the selection of separating constructions of floors and ceilings having a high reduction in impact sound. When we talk about the basic wall constructions where mineral wool is utilized, we generally have in mind these wall types. First one, the classical drywall or a gypsum wall. The next one, wall linings, so basically adding an extra layer of insulation and interior wall finish to the basic wall. And the third one, the cavity wall, where insulation layer is inserted between the two wall structures. Basic ceiling or basic floor constructions with mineral wool can again be shaped around classical concrete floors or more traditional wooden floors. An insulating layer can be added to the floor from the upper side or from below to the ceiling, as we can see in this particular image. But what is the most interesting for us are the actual acoustic effects of mineral wool. So the improvements that mineral wool brings in these constructions. Actually, one of the most often questions we face is about the actual difference in sound insulation of a certain constructions with and without the mineral wool. So let's address exactly that problem, and for the start, let's look into the effects that mineral wool has in classical drywall systems. For example, the part of this wall on the image has a mineral wool layer in the air cavity, and a small part has nothing between the steel elements. So the very legitimate question we can pose is, what is the difference in sound insulation between such two constructions? And here is the Airborne Sound insulation graph, with a reminder that the higher sound insulation value, or the higher RW value, means the more favorable acoustic result, or actually the better privacy between two spaces. So for this standard 100 mm dry wall, which has two standard 12.5 mm thick gypsum boards on each side of the wall and no mineral wool in the cavity, we expect an average value of RW of 37 decibels, with different performance across different frequencies. And now if we add the insulation, so if we fill the cavity of this wall with the mineral wool, here is what happens. So an increase in the sound insulation across the entire frequency range and an average 10 dB increase in the single number RW. So from RW of 37 decibels to an RW of 47 decibels. But please have in mind that this 10 dB increase is not a fixed value that is valid for every single wall structure. So the actual improvement will depend on the thickness of the partition or the number of gypsum board utilized. But generally, yes, there will always be an increase in the airborne sound insulation with adding the mineral wool. When we talk about sound insulation, the wall linings are also a very interesting subject, because this is the strategy which homeowners utilize to increase the poor sound insulation between themselves and the noisy neighbors. And what we see as a very common technique is a direct fixation of the gypsum board to the main wall, so as given in the image, without any insulating layer. So let us then compare the sound insulation for two wall upgrades. First one, done without the insulation, so with a direct adhesion of the gypsum board to the basic wall. This one achieves an RW value of 53 decibels. And the other solution, which includes mineral wool layer between the same basic wall and the gypsum board, achieve 61 decibels. So the benefit of utilizing mineral wool is quite evident in the entire frequency range. And finally, by utilizing mineral wool in the wall upgrade, brings an additional 8 dB increase in sound insulation. Now let's move from the walls to the floors. So we shall do the comparison against the basic floor structure, and in our case it's a simple 140 mm thick concrete floor. We shall compare acoustic performance, the impact sound insulation in this example, with the same floor construction, which has a few additional layers. An insulating layer of 30 mm Knauf insulation mineral wool, and the floor finish, which can be cement screed, parquet, or just ceramic tiles. And here is how the impact sound insulation chart looks like, with the average value of impact sound for the basic concrete slab amounting to 80 dBs. Please remember that this chart displays the impact sound, so not sound insulation. Therefore, as we said, the lower the value, the better it is. And here's what happened with the impact sound when we add the floating floor with mineral wool on top of that basic concrete floor. The reduction of the impact noise is evident across the entire frequency range, and the single number rating of impact sound has been reduced from 80 to 49 decibels, so a 31 dB reduction in impact sound. The second strategy to fight the impact noise problem, which is actually a predominant strategy for renovations of apartments, when we can approach the floor only from below, so from our side of the apartment, that is the installation of a suspended ceiling. And here is the illustration of a complete sequence of such an installation. So a 45 mm Knauf insulation mineral wool is added below the basic 140 mm concrete floor, and the ceiling is closed with a single board of a standard 12.5 mm gypsum. And here is the comparison of impact sound level for these two constructions, before and after the installation of the ceiling with the mineral wool. So there is a 23 decibel of a reduction in impact sound, from 81 decibels for a basic concrete floor down to 58 decibels to a concrete floor with the suspended ceiling. So a delta L value of 23 decibels. So all these examples that we have just seen come from the actual acoustic tests undertaken in standardized acoustic facilities, basically in the acoustic laboratories. However, there is a difference between the results obtained in these facilities and the real-life performance in buildings. And this difference in the acoustic performance between the acoustic laboratory and the construction site is often the cause of problems and disappointment with poor acoustic insulation from the homeowner's side. So this is a very complex subject, but to simplify it, I like to use the analogy of fuel consumption, because fuel consumption is something much closer to our hearts and our pockets, and all of us visit petrol stations, well, much more often than acoustic laboratories. So how does the fuel consumption work? When we buy the car, the manufacturer declares an average fuel consumption, and this consumption has been very precisely measured following a very strict text methodology. So this declared fuel consumption is something which corresponds to acoustic performance which is measured in the laboratory, with the indicators for airborne or impact sound insulation, which is on the right side of our fuel indicator. Let's say when we have a full tank. And we call these the nominal acoustic performance. On the other hand, we bought the car, now we're starting to drive the car, we immediately notice that we consume more petrol than declared by the car manufacturer. And this, in the real world, is something that we all accept as more or less normal, and we do not take car manufacturer to the court because of that. So we understand that the standard test of fuel consumption assumes constant speed, while we usually drive a bit slower or a bit faster. And that's actually what happens with the acoustic performance at the construction site. So this actual performance on the site, it's indicated with R-W and L-W on the left side of our fuel indicator. So sometimes we can build the wall perfectly, but sometimes the wall is penetrated by ducts, by pipes. Sometimes this wall carries the doors, or it just has a large TV screen built inside it. So all of these are the factors which can have endless variations that can cause difference between the nominal, the laboratory measured value of acoustic performance, and the actual value of acoustic performance which has been achieved on the construction site. And the magnitude of this degradation of acoustic performance can vary from 0 decibels, if we manage to make our installation close to perfect, or even to 20 decibels if our principal building element is severely degraded. But to illustrate that even better, let's take a look into an example of such degradation, which happens in everyday lives, and actually it's often the heart of all the complaints. So here is an office space that actually looks very nice. From architectural, from interior design point of view, we could agree it's quite a successful project. But let's now try to imagine how would this office sound. So for this particular example, I'm focusing on the sound insulation between these two offices in front of us. So a closer look at the details will let us know that the partition which separates these two offices terminates at the ceiling level. If we would open one of these ceiling tiles, there would be a large ceiling cavity expanding across the entire office space. And this ceiling cavity will most likely contain firefighting systems, air conditioning systems, electrical conduits, and other services. And from the acoustics point of view, this ceiling cavity is an opportunity, or better to call it a danger, for the phenomenon of flanking sound transmission. So flanking sound is nothing more than the sound which is transmitted around, or in our example above, the principal building element. So in our case, the partition between two offices is the principal building element, and of course we are intuitively expecting that all the sound will pass through this partition. However, in real life we end up very surprised when we figure out that we can clearly understand the colleagues on the other side of the wall because the sound is passing above the partition. So in the car owner's vocabulary, we were expecting a fuel consumption of 5 liters per 100 kilometers. And now we found out that we actually consume 15 liters per 100 kilometers. But let's switch back to the acoustics and engineering vocabulary and illustrate this example in a sectional view. So here we clearly see what's the main problem with the wall. So our carefully selected partition, which achieved RW of 60 decibel inside the acoustic laboratory, is completely out of function. Because all the sound goes above the partition, through the lightweight ceiling, or actually maybe even a perforated ceiling. And the sound reaches the other room with the actual R-W of 35 decibels. So we have a 25 decibels lower acoustic performance than we expected. A disaster. And there are no limits to the possibilities for flanking sound transmission. So flanking sound can also happen because of the penetration of surfaces. In this particular case, the architect was actually very knowledgeable, and she or he extended partition above the ceiling level to overcome that first problem. But the team which was in charge to run these services above the ceiling level was not on the same page. And of course, to make their lives easier, they have opened a considerable part of the wall to install the services. And again, the nominal sound insulating performance was degraded, and the level of privacy was not satisfactory for the end user. Sometimes such problems can occur just because of an internet cable which had to be additionally installed. So a small cable, a big hole, and a big acoustic problem. So you can imagine the disappointment of these people when they realized that their internet was now much faster, but the level of privacy was seriously degraded. And details of construction, which might seem of low importance, can also play a big part in the story of acoustic design. This example is one of the classical ones for a flanking sound transmission, which is happening around the principal building element, so around the main partition. We see a lot of these examples in the office spaces where the corridor is perceived as relatively a quiet space, because it's much easier to install the corridor wall first in its full length. This wall is done first, so with no interruptions. Then, when this wall is completed, the separating walls between the offices are built. And although these walls have been selected with insulating layer, with an extra gypsum board to provide a good level of sound insulation, in real life we will again face problem because the sound will go around the partition, not through the partition. And we will face again the degradation of the nominal acoustic performance. So in such an example, we could expect a 10 to 15 dB reduction in sound insulation from the expected laboratory value, compared to the example on the right side, where we have no degradation because the principal wall element was not interrupted. So we could go on with similar cases from the practice, but for the moment let's close this chapter and repeat the important messages. So there are two principal mechanisms of sound transfer and of sound insulation: the airborne sound and the impact sound. Mineral wool is an important part in the building elements whenever acoustic performance is important. And we should be very careful when we detail our design about the traps that flanking sound transmission can bring. And the most important of all, which we have illustrated in several examples, is that mineral wool increases the sound insulating performance of building elements. So there is an actual difference in sound insulation with solutions with and without mineral wool. And the range of Knauf insulation products which are suitable for the indoor sound applications include Knauf insulation rolls and boards for partitions, as well as Knauf insulation rolls and boards for floors and ceiling. And I emphasize that our technical teams at Knauf Insulation are always here at your disposal to carefully study each particular situation separately and advise you on the most suitable product for your particular project. The second part of the webinar is in a certain way different from the previous one. That first aspect focused on the isolation from unwanted sound. But in this part, we shall focus on the room acoustics, so on the quality of the sound within the space. But to define what do we actually mean by the quality of sound, first of all, we need to understand what happens with the sound within a space. So what happens with the sound when someone actually says a word or when someone actually plays a note on the violin? When a violin player plays a tone, sound travels in every possible direction. So sound goes forwards, backwards, up and down. And there is a component of this sound which comes to our ears first. And this component is called the direct sound. So this is the sound which traveled the shortest possible distance from the source of the sound, from the violin in our case, to the listener. And this sound traveled without any interaction with other surfaces. In a very rapid succession after this direct sound, our ears shall receive hundreds of reflections. Some of these reflections will come from the walls, some will come from the ceiling, and from the stage. Some reflections will also come from the floor and from the seats. And the synchronization of all these components will actually define the quality of the sound that we as a listener perceive. So if our ears catch some of those reflected sounds much later than the direct sound, for example 1 second later, our brain will recognize this as the echo. But if these reflected sounds arrive very quickly after the direct sound, within a few milliseconds, our brain will have a problem to recognize what was the direct sound and what was the reflected sound. And our brain will recognize it as a very rich sound and appreciate this very strong acoustic sensation. So very generally, we can say that this permanence of sound within the space and this very fine balance between the direct sound and the reflected sound defines the quality of a sound within a space. And this permanence of sound within the space is what we call the reverberation time. And this reverberation time is measured in seconds. And it's usually considered to be one of the main parameters which defines the acoustic quality of a certain space. Now, a very good question is, what is the best? What's the optimum reverberation time for a certain space? Well, I have to disappoint you, there is no straightforward answer to this question. So there are certain types of spaces where short reverberation time is preferred. So when I say short, I mean reverberation time below 1 second. So these are typically the spaces such as offices, meeting rooms or classrooms, where it is the spoken content which is predominant. So our main intention in such a space is to make the spoken content understandable. On the other hand, the spaces where music is of an importance, we benefit from a longer reverberation time, usually exceeding 1 second. So opera lovers, for example, will appreciate reverberation time of 1.5 seconds, and it is said that Mozart might sound the best with a reverberation time of 2 seconds or more. So you can see there is a very fine and fragile limit between these values, and actually that's the beauty of acoustics, because there is no strict rule what is good and what is bad. But our general idea and our target is to make the speech intelligible and to make the music strong and clear. And we use reverberation time as the convenient way to express and quantify that. Reverberation time, it's directly related to the volume of the space, therefore to the size of the space and the sound absorption of all the room surfaces. Again, this is something very intuitive, so you can imagine that the larger space will sound more reverberant, and space with more sound absorption, so with more soft elements, will sound less reverberant. And it can be easy to understand how the materials such as carpets or curtains help in controlling and in balancing reverberation time. But what is the benefit and what is the acoustic effect of mineral wool when we talk about the room acoustics? So one way of utilizing the mineral wool is to pair it with other materials which are often used in interiors, such as the ceilings. So let us take a look how mineral wool improves the acoustic performance of a ceiling, in this case a perforated ceiling. This again is the sound absorption chart for a classical perforated ceiling tile system. So this system just by itself has already a decent sound absorbing property. So if we put an average alpha value on this chart, we could say it's roughly around 0.55. In this case, we can say that because of the perforations, some of the sound is trapped in the ceiling cavity, and actually that's why the perforated ceiling provides some sound absorption by itself, unlike the standard gypsum ceiling, which would have a negligible sound absorption. So a standard gypsum ceiling would have most likely an alpha value close to zero. After adding the mineral wool insulation on top of the ceiling, here is what happens with the sound absorption. We have an increase across all the frequencies, and the average increase from 0.55 to 0.9 of the sound absorption coefficient. So these things look very straightforward, but they are often confusing, and it's not so easy to talk in the terms of alpha coefficients, of reverberation times, because even for professionals, it's not easy to imagine how would a certain space sound, even if we know the size of this space, or even if we know the characteristics of every single material we plan to utilize in this space. However, modern technology managed to overcome this communication problem. So today it's possible to simulate the acoustic conditions of any room just by having the inputs of its size and the materials used. So let's take this meeting room as a simple example. On the first look, we can notice the extensive use of glass and gypsum, and we could make an educated guess to expect around 1.1 seconds of reverberation time in such a space. But still, it's very hard to imagine how would this meeting room actually sound. So for the moment, let's technology do the work for us, and let us listen on how would a simple sentence spoken in this room sound. Luckily, we can see what has been said because it's quite difficult to understand it. And this is something that all of us would call echoic space, and actually acoustically very poor space. Although from design point of view, from the interior design, it looks quite good. As we could not have a meeting in such a space, okay, let's move to another meeting room, and this one still looks good and modern, but unlike the first one, it incorporates some mineral wool which is hidden behind these wooden slats on the side walls, and it has some mineral wool above the micro-perforated wooden ceiling panels. So for this space, with some acoustic treatment, we would expect a reverberation time of 0.6 seconds. But again, how would this meeting room actually sound? So now let's listen again to that same sentence. Well, that sounds much better now. But to use the power of mineral wool and what sound absorption can do for the acoustic quality of a space, you don't need to rely only on perforations. So there are solutions from Knauf and its partners where sound absorption can be achieved with a solid look without any perforations at all. Actually, there are no limits to your design ideas, so even the wood wool products provide exceptional sound absorption, and they look great either used on the ceilings or on the walls. So the only limit to the acoustic design is your imagination. As we have mentioned, the wood wool products, apart from using them in the interiors because they look so good, one of their typical applications is to the ceiling of underground parkings. And the reason for this particular application is actually twofold. First, to increase the sound insulation to the space located above the parking. And second, which is a very interesting aspect of room acoustics, but unfortunately very rarely discussed and often neglected, is to increase the speech intelligibility and enable the voice communication capability. And this is very important if we consider evacuation and emergency messages which are delivered through the public address system. And this is very important safety aspect, and it's tightly related to the reverberation time of large public spaces. And this is actually quite often a problem in spaces such as underground parkings, train stations, airports, or shopping malls. Very often at the airports, we are not able to understand messages which are related to departures or arrivals because of the bad acoustics. But more important would be the emergency evacuation messages whose poor intelligibility can even lead to misfortunate events. And here is a sound absorption chart for a wood wool board Tektalan by Knauf insulation compared to the aerated concrete of same thickness. So there is quite a difference between the two in the entire frequency range, and the difference of 0.6 in the average alpha value. So from 0.35 for the aerated concrete to 0.95 for tectalan, for a wood wool. So similar to wood wool, aerated concrete is also used for the ceilings of parkings. And the aerated concrete would fulfill that first part of the acoustic task to increase the sound insulation to the space above the parking. However, its low sound absorptive capacity would make the parking a very echoic space, and you would struggle to understand what has been said through the public address system. So for such large spaces, more sound absorption will lead to a lower reverberation time, and this lower reverberation time will lead to a higher speech intelligibility. And here are the important messages related to room acoustics. We've mentioned the importance of the fine balance between the direct and the reflected sound. We have discussed the need to optimize the reverberation time, keeping it a bit shorter for the spoken content and a bit longer for the music. We have discussed some strategies on how to control the reverberation time and presented unlimited design options. And finally, we've mentioned the importance of speech intelligibility in large public spaces and the advantages that wood solutions can offer in such applications. So what to capture is that mineral wool adds additional sound absorption to the space and aids in reducing the reverberation time. There are numerous products in the range of Knauf insulation which can be utilized for the purpose of reverberation time control, such as the wood wool boards suitable for exposed ceilings, especially underground parkings, or the classical insulation rolls and boards used for ceilings and walls. But let's now move from the interior of the building to the building envelope. And let's talk about the third aspect of the acoustic design, the insulation from outdoor noise. Some of us are very lucky to live in isolated and remote individual houses. And for such objects, the outdoor noise is actually not even an issue. But apart from those few very lucky individuals, the world is becoming more and more densely populated. So there is more and more people on the planet, and more people are moving to the cities. So we could generally say that our future has a more urban than a rural perspective. And this is how this urban perspective looks like in Hong Kong. This is maybe a bit of an over-exaggerated example, but a good example to imagine the levels of noise which might be present in such a dense urban environment. And typical sources of outdoor noise are traffic, which can include road noise, trains or aircrafts, then the various building services, which are often installed on the roofs of neighboring buildings. Outdoor noise can also be emitted from industrial sites and production facilities, which are quite often causing the problems to residential areas, or even the entertainment noise, such as the noise related to sports events, stadium rock concerts, various outdoor events, or just simple nightclubs. And to give you an idea about the magnitude of noise in a typical urban environment, which usually consists of a mix of traffic sounds, human conversation, and some building services noise, that typically amounts to 65 to 70 decibels. On the opposite end of this scale is something which we can consider as a comfortable interior level. And this ranges between 30 and 40 decibels. Let's say that 30 decibels would be quite a good level for a bedroom, and 40 decibels would be quite a comfortable level for a working space or an office. And our first weapon as designers, our design strategy against the outdoor noise is so-called shielding of noise-sensitive areas. So noise-sensitive areas would be rooms such as bedrooms, hotel rooms, maybe libraries, and similar spaces where rest or concentration is important. So shielding would then imply a careful arrangement of these areas, so not to locate them close to main roads or to neighbors' air conditioning units, or basically away from any similar noisy hotspot which might be problematic for our facade. And this is something very intuitive and very effective as a design trick, but we don't always have the commodity to locate all the noise-sensitive areas where we would want to. Because sometimes our balcony and bedroom inevitably ends up facing the main street, the train station, or just some simple noisy object like maybe a car wash station in front of our home. And in those cases, we do have to apply some acoustic strategies. Generally, we differentiate two acoustic strategies. First one is the noise reduction at the source of noise, and the second one, which is interesting for us when we discuss the building facade, is the noise reduction at the building envelope and the design of suitable facade elements. Here's a quick and simple illustration of the standard facade elements. So our first line of defense against the noise from outdoors is pitched roof, a flat roof, contact facade or the attic system, and ventilated facade. So what are the effects that mineral wool has in a facade system? So let us look into the external wall, which is usually our first line of defense. For example, we have a concrete wall as our basic wall construction. The sound insulation, the RW of such a wall, amounts to 59 decibels. And let's not forget that the higher the RW is the better when we are discussing the matters of airborne sound insulation. And noise from outdoors falls into the category of airborne sound insulation. So this is how the sound insulation graph of our base wall, the external concrete wall, looks like, with the RW value of 59 decibels. If we add the facade system, the attic system with mineral wool to the external wall, we will provide an increase in airborne sound insulation, so the increase in RW value of 11 decibels, from 59 to 70. To make things a bit more interesting, let's now add to the same graph the attic system of a same insulation added to the same base wall, but this time based on EPS insulation, on the polystyrene. So we can immediately notice something very strange. So sound insulation of the basic wall is now reduced in the lower frequency range, and this eventually causes the single number rating, the RW, to fall by 3 dBs. So from 56 to 59. And this reduction in the lower frequency matches the frequency of that hum that the traffic noise usually produces. So eventually, instead of increasing the sound insulation of the external wall, which would be intuitive because we are adding extra layers of insulation, we actually reduce the sound insulation of the external wall, and we actually reduce it exactly in that frequency where traffic noise is usually the most predominant and most annoying. So this particular effect of reducing acoustic performance of the basic wall is directly related to the rigidity of the insulating layer. So this example outlines the difference between insulation such as mineral wool, which has more open pore structure, and in this example the polystyrene, which is generally more rigid and has a more closed pore structure. But now we could imagine a large variety of materials which would fit between these two curves. So some materials could increase and the other materials could decrease the sound insulation of the basic wall. So again, we're coming to that story that there is no the best material for every single purpose. Rather, there are materials which are the most suitable for a certain application. Here is another example of effects of mineral wool in facades. And this time we can illustrate it on a wooden structure, which is becoming very attractive these days because of its appearance, the green building story, and the energy efficiency. And in this case, our basic wall is a cross-laminated solid wood structure with an RW value of 34 decibels. And if we plot this wall on the sound insulation chart, here is how the curve of 34 decibels looks like. We can again see that addition of the insulating layer causes the sound insulation to rise, again across the entire frequency range, with an overall increase of 28 decibels. So from an RW value of 34 for the basic wall to an RW value of 62 decibels to an isolated basic wall. And this is actually how this particular construction looks like. So on the inner side, to the interior of the building, we have a 40 mm insulation board with 2 standard gypsum boards, and on the outer side of the basic wooden element is a 100 mm thick insulation board with a facade coating. So we're talking about a complete facade system. For the very end of this fundamental aspect of acoustic design, which is outdoor noise, one particular aspect which does not often cross our minds when we start with the design process, the rain noise. And the rain noise is the most prominent on metal deck roofs. So actually, the aspect of rain noise is even regulated in some countries, but regardless of that, rain noise can be quite annoying if you happen to live in the attic, just below the metal deck roof. And these kind of constructions are these days very popular for schools and even multi-purpose halls. So now you can imagine it would not be easy to listen to the lecture in a classroom or to a classical music concert in a multi-purpose hall if it happens to be on a very rainy day. So rain noise is maybe not on our minds as a designers quite often, but we still take it quite seriously, and actually we do perform acoustic tests to measure the impact that rain noise has. And in one of the studies which was undertaken recently, rain noise on two roofs was compared. And as we're talking about the noise level, the lower value is more favorable. So a typical metal construction, such as this one, insulated with Knauf insulation mineral wool, yielded the result of 35 decibels once it was exposed to rain. And the rain noise for the similar roof construction, but using the foam as the insulating layer, produced 60 decibel in the space below the roof. So 25 decibels more noise compared to the roof with a mineral wool solution. And again, it's the porous structure of the mineral wool, the principal reason for the improved acoustic performance, even in this very particular application. And in the end, to summarize what we've learned about the insulation from outdoor noise. So typical outdoor noise levels are in the range of 65 to 70 decibels in standard urban areas. Comfortable interior noise levels range somewhere between 30 and 40 decibels, and the building envelope is that element which actually presents the barrier between outdoor noise level and indoor level of acoustic comfort. With several real-life examples and actual constructions, we have also outlined that the correct selection of insulating layer increases sound insulation of facade system or even reduces the level of rain noise. But on the other hand, we also did see that misfortunate selection of insulating material can sometimes lead to a reduction of sound insulation. At Knauf Insulation, we provide a wide range of products which are suitable for all the facade elements. Such are the insulating boards for contact facades, rolls for pitched roofs with our ECOS technology using the bio-based binder, or boards for flat roofs. And the most important is that we do have the knowledge and we do have the experience to advise you on the optimum solution for each particular facade type, depending on the requirements and your ideas behind every individual project. So part 4, the fourth fundamental aspect of the acoustic design, noise of building services. So there are numerous types of building services, and eventually in real life we can even experience noise with the simple buzz of a light bulb. But generally, there are certain building services which are considered as the main sources of noise and the main sources of potential problems. These are typically the elevators, the plumbing systems, air conditioning units, or complete equipment rooms, which can house anything from central climatization systems to swimming pool pumps. I'll start with the elevator's noise, as I've personally lived in a lot of buildings and I've spent nights in many hotels where I could hear every single stop and start of the elevator. So the principal design strategy when designing the elevators is to separate the elevator, so the elevator shaft wall, from the noise-sensitive area. Again, if we are limited with options and we can't escape from these situations, the correct acoustic strategy would be to structurally disconnect the common wall between the room and the elevator shaft, because that's the wall which usually has a very large surface and transmits the sound from the elevator's movement to our ears. And a very similar problem happens as well in the case of equipment rooms, which are located next to the residential areas. And here is a layout for one typical residential building. So we can notice the central core, which houses 4 elevators, and the staircase, with residential spaces located around the core. So these upper three elevators are very favorably located. They are next to the corridor, they are next on the utility space to the right, but this fourth elevator looks like a problem because it shares a wall with the living room and it shares the wall with the bedroom of these two neighboring apartments. So this is something which can pass relatively unnoticed during the design stage, but in the end, if this building opens, the tenants would most likely complain about the noise coming from this elevator. So how to solve such a problem? Generally, we classify such a challenge into the category of wall linings or wall upgrades, but with the very important detail of structural disconnection between this wall lining and the elevator shaft. Such disconnection can be achieved with special brackets or just by connecting support steel structure to the floor and the ceiling alone with the mandatory insulation layer of mineral wool and additional wall boards. So this upgrade will certainly reduce the problem, but there is still a path for the noise transfer with the connection of the elevator to the floor slabs. And these particular details are very difficult to solve during the renovation. Although, yes, we could introduce a secondary ceiling, a floating floor, and achieve complete and much better insulation. But better solutions can be done in the early design stages. And that's a very important message, that acoustic solutions are much more easier to implement and much cheaper if they are considered in the early design stages. That's why for every architect, it's important to have a strong partner, a strong technical team with a wide range of acoustic solutions from day one of your design process. Another usual problem with building systems are the plumbing noise issues. And this noise is usually related to the water supply and drainage systems. So the most simple case would involve us hearing the neighbors when they take the shower or flush the toilet. So in this illustration, we can realize the benefit of a structural decoupling with mineral wool, which is actually preventing the water flow to be transmitted to the pipe and from the pipe to the entire building structure, in case we had a rigid fixation, if this mineral wool strip was missing. So plumbing sound, in that case, could easily travel up and down the building, even through several floors. So to summarize this part of the noise of building services, we have highlighted the importance of a structural disconnection and mineral wool infills. But again, owing to its porous structure, mineral wool is highly effective in reducing noise levels of building services, as well as aids in the structural disconnection of building elements. And Knauf insulation products suitable for these applications are Thermatech and PowerTech rolls and boards, which are great for applications where the space constraint is an issue. And they are also suitable for application around the pipework and ventilation channels, as well as our traditional Knauf insulation rolls and boards for partitions, so basically for wall linings and wall upgrades. After protecting ourselves from the outdoor noise, now we shall take a look on how to protect others from the noise that we and our project might be creating and introducing into the environment. For a good illustration, let's again use an example of a densely built area. And if you look very closely at these facades, you will notice that there is at least one air conditioning unit for each apartment. And in this case, it's these window types air conditioning units, which are maybe amongst the, well, noisiest units out there, but still they're used across the world. So you can imagine how horrible this entire space, this entire internal courtyard sounds when all of these air conditioning units are working at the same time. So typical sources of noise which cause impact to the environment are air conditioning units and various items of mechanical equipment. This can be from pumps to heat exchangers, exhaust fans, and usually these are located in the equipment rooms, which will have some openings on the facade, typically for air intake, or generally on the roofs of our objects. And it's not so grateful to give an estimate of typical noise levels which is produced by these sources, because they're all very much different between themselves. But often, especially in the case of mechanical equipment, more important than this average noise level is even tonal noise. So basically a certain tonal component which drives everyone crazy, a certain frequency, certain buzz, just a certain pitch of the sound which is particular for every single item of equipment. And how do we fight such problems? Well, in the previous chapter we have focused on noise reduction at the level of the building envelope, but now we resort to the strategy of reducing the noise at the source of the problem itself. So from a design perspective, that would mean doing our best, usually together in coordination with mechanical engineers, to locate the items of equipment which shall be noisy away from noise-sensitive area. So basically away from our own bedroom and away from the neighbors. Good locations are usually the nearby main roads or open roads. However, when we can't avoid certain impact to the environment, we do have to think about certain acoustic solution. This is a good illustration of what reducing the noise at the source actually means. So our insulation is very often used to fabricate casings and enclosures for the equipment. It's often used as the acoustic infill for sound attenuators, or it's used inside the acoustic louvers, which enable the circulation of air but still reduce the noise level which we emit into the environment. And all this noise reduction happens exactly because of the high sound absorption that mineral wool provides. Because as we force the air and the sound to go through a certain space, which is padded, which is lined with the mineral wool, sound tends to get reduced. Here is one such solution implemented at our own factory in Slovenia, where relatively a simple elbow padded with mineral wool insulation prevented the noise to be transmitted from the fan, which is located behind this elbow, to the neighbors. So our insulation can be easily shaped to fit any custom solution, and that's why it is so useful for such tailored applications. And on this particular example, you can notice that the finishing of the insulating layer is black. That's because of the facing which is applied to the insulation. And this particular facing has been applied to prevent mitigations of fibers due to the airflow. So it's often the case that apart from noise pollution, we need to consider health or hygienic requirements too. So what's important to capture from this story about the noise impact to the environment is that the most effective strategy of mitigating the noise is if we reduce it at the source itself. And for these particular purposes, typical acoustic measures include acoustic barriers, acoustic enclosures, the blankets, or some more complicated devices like sound attenuators or acoustic louvers. And from the design and coordination point of view, locating the noisy equipment as far as possible from noise-sensitive areas is always a good choice. And in all these applications, it's again mineral wool that aids in reducing the noise levels emitted into the environment. So for this particular application, we at Knauf Insulation have a dedicated range of products for technical solutions. So these are our Thermotech and PowerTech insulations, which are generally very easy to shape. So their installation is very easy. And usually these applications happen to be in a very constrained spaces. So it's also possible to fabricate all these products with a variety of facings which are suitable for every particular application. And this brings us to the end of our webinar. I hope that you enjoyed it and you've gained a lot of new and useful information about the acoustics. I'm also hopeful that you will revisit the webinar and use it in your daily work when you face an acoustic challenge. We at Knauf Insulation are always here at your disposal and ready to help you and assist with any acoustic problems or challenges you might face in the future. Thank you.